All right, folks, I'd like to go ahead and get started right now. My name's Nick Weddles, and I was with the NASA Jet Propulsion Lab up until very recently. I decided to roll the dice with a startup company. I'm just going to cover some ground rules real quick, then we'll kick it off with our keynote speaker. So if you are even numbered, please be on this side, and if you are odd numbered, please be on this side to facilitate setup. We have a 3-minute hard stop, so we're going to go right from talk to talk, so please hold your applause. And but do not hold your applause for this gentleman. So I'd like to introduce our keynote speaker. In addition to being part of my PhD committee a few years ago, he's the co-founder of the International Conference on Robotic Humanoids, Humanoid Robotics, and Robotic Science and Systems. He's co-authored more than 300 conference papers and journal articles. And when he's not doing that, he's a founding director of the Max Planck Institute for Intelligent Systems and a professor of computer science, biomedical engineering, and neuroscience at the University of Southern California, my alma mater, Stefan Schall.
Thank you, Ben. This is loud. Thanks a lot for the introduction, and thanks for the organizers inviting me here. I have 20 minutes. Is it running now? Okay, yes, my 20 minutes are running. And what I try to do is just give you something which is a little bit more of a vision. This is not really research which is fully developed or which I fully understand, but rather something which I think it's important. And we'll see whether you like it or not, but it's just some, thoughts. So it's about perception, action, learning, and associative skill memories, and you will understand in a second what that will mean. Very important, okay? Lots of people contribute to this work, and I will not mention them in detail, but they're all there. So where to get started? Animals, the nature kingdom. Lots of cool little things. They might be tiny, they might be medium-sized, they may be really big, and they all work amazingly well. And they have one thing in common. So what do they all do? They essentially perceive the world, they act on the world, and they learn and adapt. In some sense, this is a very primitive definition of what you might want to call an autonomous system or an intelligent system. And what we try to do in technology and robotics is we try to create systems, oops, does that work? Yay. Which are similar to that. There's the world of micro robots or nano robots, there's intermediate size robots, there's big robots, there's in-car robots, industrial robots, or whatever. And these systems have the same property in the end. We would like them to perceive the world, to act in the world, and to learn. It's the same circle. So this is kind of the basic principle of a system which can do something by itself in this world. And we can formalize that, so this is also not too hard. This is now typical control diagrams. So we have some action generation mechanism, we have a system and environment which we try to control, we have some feedback sensors, we have noise, and we have some learning system which tries to make this get better over time. Now, this is essentially what we should all be working on. But what is essentially more, let me just skip over that, is that most of the world in robotics, or in many sciences, we like to try to put things into little boxes and just focus on that. So there's the action people, and there's the perception people, and there's the learning people. And if you really look, that most of the people do just research within their little box. And then occasionally they talk and hope that things come together. But this may actually be a problem in robotics for the future. And what we should look much more for is that we get more people who understand at least a little bit of all of these boxes, who can really address action, perception, and learning. Since if you do perception for action generation, that is different than just doing perception. If you do actions in order to perceive better, that's also something totally different. And if you add learning to this entire loop, and it's a loop which has stability properties, everything may be falling apart. And the question is basically, how can we go away from this very specialized thinking to a broader thinking where you really put the loop together and see what can be done? So let me show you an example from our own research from some time ago. And I'm sure whether this video starts running. It does. So this was actually a gorgeous little project that was learning locomotion with a little robot, little dog, about this big, not as big as Big Dog. And this was a program which was designed to be really purely action-oriented. Perception was done by a Vicon system, so we have the little silver markers on the system. We don't have to do perception of that. We don't have to do terrain perception since we got CAD models of the floor. And we could totally focus on control and planning and nothing else but that. And it was actually a cool project. It took about 4 or 5 years, and it was in some sense very successful. And there's lots of different groups who worked on that. They have all the same kind of videos. I just show you what we generated at the end of that. But in some sense, this is also wrong, since we just addressed a tiny little project of control and planning and be completely in the control world. So how to get a little bit away from that? So here's something which I found interesting some years ago, and that's actually a science paper by Tom Mitchell. If you don't know Tom Mitchell, he's a very established researcher in machine learning, has co-authored a couple of books. And they basically published a paper where they try to figure out how nouns elicit brain activity in the human brain. And they use some machine learning techniques in order to basically figure out what's going on in the brain. But there was this one really important thing, which is absolutely trivial and still good to recall occasionally. Like one little noun, like celery, will actually elicit a lot of activity of associated things, like that this is a vegetable, and maybe that it's green, or what taste it has, or whatever. So the brain always turns on lots of things. In the same way, you see something that looks pink, and you say, oh, this smells most likely sweet. There's these associations we have. It is never just one thing by itself. There's lots of things which get connected. And the question is, isn't that this kind of associative element in the brain, this associative element which we should also have potentially in our robots, isn't that something we should try to work on and think more about? And that would maybe bring together perception, action, and learning in a different way. So let me try to make this a little bit more crisp. So here is a very simple model of how a robotic system, for instance, may develop over time. So it is in a particular state X at time t. There is a desired state with a little d. And basically, this will elicit an action, and this action takes me to the next state. And at the next state, I have a new desired state. So this is just a normal evolution of over time of a controlled system. Nothing profound. Now, this is in some sense what we've been doing a lot. But now it becomes more interesting when you say, okay, when you're doing this, and you have a more interesting robot which actually has a lot of sensors, like tactile sensors, auditory sensation, vision sensors, whatever sensors you want. That means with every time slice now, you actually start to get sensations, a lot of sensations. Just recall, so in the human brain, in the cerebellum, every Purkinje cell, whatever, gets on the order of 100,000 to 200,000 inputs. Now, this is a real lot. But maybe we can get to the idea that at some point we have so sensor-rich robots that we have really hundreds of thousands of inputs. And these inputs are actually meaningful. They're actually meaningful under one particular assumption. That is, if you do movements in a stereotypic way, that means if I'm reaching for a cup, I'm doing this like this. I'm not doing this like this today, and I'm not going around my head 5 times before I go there. I just do it like this, boring self as I am. Always the same way. But when I do this like this, my sensor experiences will also be the same. So it means I can do some simple statistics about these sensory experiences. And it means with a particular motor skill, which is shown here in this little graphical model, and I can start remembering what I should feel, see, hear, or whatsoever, and can use that actually at some point as a standard and say, if I don't feel and see that, something is wrong. And all of you know that. Everybody knows the experience. You walk through whatever on the pavement. There's a hole. You don't see it. You step in the hole. Before you step really full in the hole, you know it went wrong. And you immediately start some recovery action. We predict all the time what's going to happen. We always know what should be there. And this then basically gives me, at some point, if I start remembering these sensory traces, I can actually then see what I should feel, so this is now my desired sensory trace, and what I actually experience, and then I see an error, and I can use this error, for instance, for correcting my motor commands, for switching behaviors, for aborting entirely and just doing something which is appropriate, rather than blindly running into the wall and experiencing, oops, I'm broken. So let me show you some examples where we try to get our fingers on that. This is an older video done by Peter Pasta, Mrinal Kalakrishnan, and Sachin Chida at Willow Garage some time ago. And so this was a task using the PR2, which has nice little sensory pads, tactile pads. And the robot just learns with a reinforcement learning algorithm how to flip a cube. The cube is equipped with an IMU, so you can actually figure out whether it's flipped or not. And it takes whatever, 50, 60 trials until this robot can do this with chopsticks. And was really meant to be a toy task to get interesting sensory experiences. And you see kind of how the touch sensors light up. It's about, whatever, 100, 110 touch sensors. And after a while, the robot can do that, and then it can do it repeatedly. And then you can actually start, okay, now I've learned a motor skill, but I also learned to associate a large number of sensory traces with that. And this is just showing that this is actually not so easy. So people trying to do it with the PR2 hands have a really hard time. It's kind of fun. Okay. So what you get, and this is just a snapshot of now 8 sensory traces from these 110. You basically get over the successful trials the green data, and you get trajectories over time. These are just, forget about what the vertical axis is. This is just some activation of the tactile sensors. Time is in the horizontal axis. And you get the red traces, which are failures. And then you can have simple statistics. You know, basically take the mean, you take a variance, so you get basically a mean trace, and you get something like a confidence interval. And then you can basically say, okay, after I learned that, can I use that to actually monitor my own behavior and actually even predict that I'm going to fail before I fail? And this was then done with a couple of training data trials. And this is basically, again, here the red trials are the failures. And you see very early, before the movement is done, before you actually try to fulfill the skill, that when you get out of the confidence intervals, you know that something is going wrong and you abort, which is great. Just not running into the wall is really great. And I just have this little example all the time. So if you have a little kid, like a 4 or 5 year old, and you throw the kid a ball, the kid is just there, has the hands out, and if you hit the hands, it will catch the ball. If you don't hit the hands, it will just don't do anything. When they're about 7 or 8 years old, they suddenly do very fast actions to catch the ball. But they know initially that they don't trust their own skills. And they only use it later when they are more skillful and more basically attuned to their system. This is something which we would like to exploit. So we call this associative skill memories. We don't know a better name for that. But it's essentially now the idea that we have motor components, we have sensory components which are learned, which are desired components, and we compare them against what's actually happening and then try to act accordingly. And the actions from our point of view are either to abort, to switch to something else, or to use the mismatch between what you feel and what you want to feel to correct the motor command. So the latter one is actually a nice little piece of work which, again, Peter Pasta, Ludovic Righetti, Mrinal Kalakrishnan did some years ago. So here this is basically teaching from demonstration how to pick up this flashlight. And it's just taught, then the robot does it a couple of times. It basically generates a associative skill memory. It knows what to expect from all sensations. And then you can actually feed this back. In this case, we basically, if something doesn't feel right, it gets fed back into the system as an error. It gets fed back in a planning level and in a force control level. And as you can see, if it's done right, the robot can actually account for a huge error in perception. What I didn't show you here, the flashlight is perceived here on the on the blue spot, and it is actually 15 centimeters displaced. And only by touch sensation, the robot basically notices that things don't feel right, so I have to curl around, I have to do a corrective movement, and grabs this flashlight, and it works. So what does this look like? We don't really know how to plot that, but you can plot it if you want as an image over time. So basically, here's your samples, basically all the data traces you get. You can normalize them that they are between 0 and 1. That usually makes sense. And here you just see a small subset of all kinds of torque sensors, position sensors, velocity sensors, whatever. And this is maybe not the right way of plotting it, since it's really not a 2D image in the sense of kind of visual processing of images. But still, it's kind of an interesting thing where you can see that there's something going wrong, or something right, I don't know, but there are events. And trying to understand what these events mean is something which we haven't figured out yet, but we're working on that. And some of my colleagues in machine learning actually find this very interesting in order to try to figure out causality. Can we somehow say that this little red blob is actually responsible for creating this up here at some point? Can we actually reason that something which happens here will already mean we're going to fail, and we should change and we should do something better? One thing which we can do with that is, when we get this very sensor-rich representation of what we're doing, we can actually start to do a little bit more intelligent sequencing of actions. And this is shown in the following video. Now, this video was a manipulation task, which was about screwing a lid on a bottle and then screwing it off again. Now, each subcomponent of that sequential movement system was taught by demonstration with multiple trials, so you get statistics. And so what we knew a little bit from that was essentially which motion or which primitive or which associative skill memory is connected to which one. But often there might be from one a possibility to branch out to 2 or 3 other behaviors, for instance, if you need a recovery behavior. And then with some statistical processing, now purely based on these demonstrated associative skill memories, it was actually possible to automatically learn with machine learning techniques, very simple actually, kind of Bayesian, simple Bayesian, naive Bayesian classifiers, how to branch into a recovery behavior if something goes wrong, how to branch to the next sequential step of the movement until everything is done. I cannot explain the entire video here, this would take too much time, but what you can see is essentially there's also perturbations which happen. When there's perturbations, you get actually these red traces going up telling you something weird is happening. So the robot notices that. There's even acoustic perception in this video, so now you see some clapping, and when there's clapping, you also get that in the data trace. It has nothing to do with the task, but acoustic perception often can tell you that something goes wrong, like a cap falls down on the table or something like that. And suddenly, basically, purely from teaching from demonstration, it was possible without any if-then statements, any kind of state machine induction, to basically create a fairly complicated and a fairly dexterous behavior. So putting this lid on this bottle is not so trivial. It requires dexterity. And it's kind of a nice example now for this kind of automatic sequencing you can get out of associative skill memories. Okay. Yeah, I'm getting to an end. So all of these things got actually, this is now sped up into a bigger scenario which was the DARPA ARM project, which was about manipulating a complete scenario of some stuff being in a bag. You have to open the bag, and there's a weird box which has a strange little cable attached to it, which needs to be cut. And this, what you see here, is a really complex behavior which took a long time to get going. It has elements of those associative skill memories. Not all of that is without if-then statements, unfortunately. What I showed you in the previous video was really without if-then statement. It was completely data-driven. Here is much more human intelligence also inserted into the programming. But it gets a little bit to the idea that you can do more complicated manipulation tasks, like again here, opening a zipper. This is nothing which is a deterministic movement. This is really a tactile perception, and you can feel if a zipper gets stuck. Everybody knows how it feels when a zipper gets stuck. It's like, it doesn't feel well. I have enough time, I think, to let this run, and then I'm having my last slide. So you can see, basically, when it comes to all these kind of complicated finger movements, that is not easily automatically generated. So what's in the bag? Something good. Yay, found a cutter. There was nothing else in there. So originally there was meant to be more in there, but that was kind of hopeless. The bag was not needed anymore, obviously. Now then, cutting actually with that cutter turns out to be a little painful. You have two arms, and actually the two arms have a big workspace each by themselves, but if you then use them together to manipulate this thing, the workspace becomes awfully small. And the green wire will be, hopefully, first it needs to be perceived. I'm doing perfect on time. And come on, we've got to cut it. It's important. Otherwise, it's unsatisfying. Yes, good. Fine. I'm happy. All right, and that brings me to the end. So it's a little bit of a different view of trying to get action perception and learning together, and trying to create very rich representations, which then may allow these associative skill memories, finding causality, figuring out how to put in more visual features, automatic creation of state machines or manipulation graphs, as we call them, and working much more with real data rather than with if-then statements. Thank you very much.
All right, thank you, Dr. Shaw. That was a great. All right, we're going to roll right into the 3-minute talks. Are you all set up?
Yep.
Okay, great. And I'll remind you we're on a tight schedule, so please hold your applause till the end. All right, whenever you're ready.
Good afternoon, everyone. So I'm Atsutoshi Ikeda from Nara Institute of Science and Technology. Today I will show about remote control system for multiple mobile robots using touch panel interface and autonomous mobility. So actually this work was done by Mr. Ochiai, Professor Takemura and Professor Takamatsu, but unfortunately, so they cannot come to Chicago, so I will introduce our work instead of them. So generally, the difficulty of the remote control of the mobile robot is an operator need to focus on to control one robot. So also an operator can get the camera image or map of the robot and very small information from the robot. So in our system, the remote control system is depend on real-time interaction between mobile robot and an operator. So the SRAM and path planning is solved on the mobile robot computer, and the user can get the estimated map, which calculated on the mobile robot, and then an operator can teach them by a point and destination using a touch panel interface. I can show the videos to describe the overview of our system. Okay, so the mobile robot is the moving depend on the SRAM using L0 norm minimization. So that this algorithm is proposed in 2011, maybe in other papers, in other paper. And also an operator can teach by a point and the destination of the mobile robot using touch panel system. And the robot try to follow the buyer point and the destination using RLT. And an operator don't need to focus on one robot because after teaching by a point and destination for one robot, the robot can follow that route, and then an operator can move on to the other robot, and an operator can control multiple robots. So we checked the traveling time using our method and the gamepad and compared these methods. And our method is reducing traveling time. So thank you for your attention, and please come to my interactive session. Thank you.
Hey. Hello, my name is Brian Colton. I'm from Carnegie Mellon University. This work on ride sharing with passenger transfers was done together with my advisor, Manuel Veloso. So here we're looking in pickup and delivery problems, where we have a group of robots or vehicles that need to transport items from pickoff locations to drop-off locations, minimizing the transportation costs. So we have to find a schedule of which robot's going to take which item at which time, in which order. So some examples include transporting people with taxis or ride-sharing systems, robots indoors delivering items for people in office buildings, mail and courier services, and warehouse automation. So here's an example. We have two robots which need to pick up 4 letters and deliver them to the corresponding mailboxes. One solution would be to have each robot pick up the letters closest to it and go to each set of mailboxes in turn. So this solution, the robots travel 8 units of distance and it takes 4 units of time. However, if you think about it, there's a more efficient way to do this. If the robots meet in the center, transfer 2 of the items between each other, then they only have to go to 1 mailbox each. So we have both the distance and the time it takes to make these deliveries. And that's the central idea of this work, to incorporate transfers into schedules. And the goal is to do fast heuristic scheduling that run in a matter of seconds or minutes. So to do this, we aren't going to be able to search over the entire space because we could insert a transfer point anywhere in this schedule and the possibilities expand exponentially. Instead, we're going to split existing deliveries which are already in the schedule. So we'll add an item, this green item in the picture below, to a schedule without transfers. Then we'll recursively split the transport of that items with other vehicles. So here we'll add transfer points into the red vehicle schedule where we'll take the item. And we won't reorder the existing actions in the schedule. It makes this search more feasible, but may miss some solutions. So we apply two heuristics using this other heuristic. We have a greedy approach where we iteratively find the best transport split for each item. We also have an auction approach where the items place bids on vehicles to split their delivery with. We also have another slightly less greedy graph algorithm where we find the best series of transfers to insert a single item with into the schedule. And if you come talk to me tomorrow, I'll give you more details about these algorithms. So we ran this on some experiments set up in a Euclidean plane. The graph algorithm had the lowest cost, the auctions cost a bit more, and the greedy was more expensive. But the cost is lower and time for better quality, lower quality solutions. They all outperformed the algorithms without transfers of similar quality. We also ran this on San Francisco using actual taxi cab data from real people. And again, transfers outperformed the algorithm without transfers. So thank you for listening. Come talk to me tomorrow morning. Thank you.
Hello, my name is Luis Yoichi Morales. I come from ATR in Kyoto, Japan. I will talk to you about our work titled Modeling of Human Velocity Habituation for a Robotic Wheelchair. Well, we know that vehicles can safely navigate free from collisions, but the real question is how can you navigate in human comfortable manner? And what would be, for example, an appropriate velocity for our vehicles? And what would happen when humans get used to the vehicle's velocity? So in this work, we propose a model for human habituation while riding a robotic wheelchair. By habituation, we mean the behavioral response decrement that results from repeated exposure to a stimulus. And we define human navigation habituation in terms of preferred linear velocity based on the experience of the user. For example, we usually set up our robots to run at certain velocity, which we think might be comfortable, but really humans start, when they are beginners, they start slowly, and as they get experience, they go higher and higher until they achieve some comfortable level, which is what we want to achieve. By preferred velocity, we know that preferred velocity changes as humans get used to it. So usually inexperienced users prefer to ride at a slow, moderate pace, but as you get used to it, the longer you ride it, you prefer to speed up to a certain comfort level, and you find slower velocities to be tediously slow. So in this work, we use a robotic wheelchair which has joystick and wheel encoders. And we use laser rangefinders to map and localize ourselves. And to evaluate the human's comfort level or excitement, we use some galvanic skin response sensor. First, we let some users drive in the wheelchair in a square loop in an indoor corridor environment, and we extracted all the data we could of their driving style. And then finally, we built our habituation model, and we compare it. This is an example of a fixed velocity wheelchair running at slow velocity approach, where we tested with 15 different participants, and we are measuring skin conductance on their hands. And well, we finally compared the habituation model that we developed with two approaches, fast at 1.6 meters per second and moderate 0.6 meters per second. We performed two types of measurements, normal questionnaires, as people usually do in HRI, and we also thought that measuring something subjective like a galvanic skin conductance measurement. Oh, these are opposite, I'm sorry. So participant feedback demonstrated preference for habituation velocity control over fixed velocity control. Well, thank you, and I'm looking forward to see you tomorrow morning if you have any additional questions.
Hello everyone, I'm Chie Hieda from the University of Electrocommunications. Today I'd like to talk about physical embodied communication between robots and children. In the area of the HRI, robots that can communicate with children have been extensively investigated. In particular, it's difficult to make children be frank if he starts to reverse the partner. So it is important how robots behave for children at their first meeting. We hypothesize that physical embodied communication, such as walking hand in hand, improves the relationship between robots and children. Because clinical psychology has shown that walking hand in hand has positive effects such as here. In order to test this hypothesis, we observed the course of the communication between robots and children after walking hand in hand. The kindergarten teacher remotely controls this humanoid robot. And the experiment was designed to examine one-on-one communication between children and the robot. We asked 37 children whose ages from 5 to 6 years old to play with the robot. We divided the children into an experimental group and a control group. In the experimental group, the robot and the child worked together hand in hand at first. Each child played with the robot for about 30 minutes at children's kindergarten. In the experiment, we recorded various data such as here. We validate the difference of intimacy by holding hands using this data. As a result, we found that the children in the control group observed the robot from a distance. On the other hand, the children in the experimental group gazed at the robot even at a close range. Besides, many positive results which support our hypothesis are obtained. The result of the experiment clearly shows that a good relationship can be built between a robot and a child when the child works hand in hand with the robot in the early stage of interaction. Thank you for listening.
Good afternoon, I'm Anne Spallanzani, and I will present a work that have been done by Arturo Escobedo, myself, and Christian Logier from INRIA in France. And the main idea of this work is to try to understand what are the user intentions when the user drives a wheelchair, so maybe we can help him to drive this wheelchair. So we try to find a way to drive a wheelchair with minimum inputs from the user, and using model of intention to understand the desired destination of the user. So we have some simple input commands, such as face pose and keywords, or gesture, or joystick, and knowledge of the user's habits. And we need some social scene understanding and social convention modeling. And while we have the desired destination estimated, we can move the wheelchair autonomously using a classical planning algorithm. We intend as user intention some destination, which can be static or dynamic. So for static destination, we can observe environments that are public zones or apartments, and observe what people do, because people do not move at random. And we can extract some typical destination. We can compute the probability to go from one destination to another, and we can use it in our user model. We can also integrate some social information, so we can detect people or group of people interacting, and using proxemics models so that when the user wants to reach a person or a group, we can find the position where the wheelchair can go to be socially compliant and accepted by the user. So the idea is that when the user gives a command, an order to the wheelchair, go here, we can compute regarding his position, his order, the user habits, and what he has done before, what is the more probable destination, and plan towards this destination. We use also keywords to distinguish between going to a static destination or a dynamic destination, using or go or join, go to a static destination, so that for a same order, with a go destination, the wheelchair will go to a door, that is the left video, and with a joint keyword, the wheelchair will go to the two person interacting. To model all this stuff, we're using dynamic Bayesian network. Thank you.
So thank you. My name is Gal Kaminka. I'm from Bar-Ilan University. This is work done jointly with David Sarne and Shachar Kosti. Both of them are also from the university. And I'm here to talk to you about interfaces for mixed initiative search. Mixed initiative search is a task where robots explore autonomously, but the human is required in the loop to identify targets. And in fact, in most applications of robotics today where robots are used, they're either teleoperated. Even in cases where they're autonomously used, we use mixed initiative search for the user to identify targets. The most common application for this that people talk about is urban search and rescue, but there are many others. The human-robot interaction question here deals with what type of interface we want to use. And there are, in fact, two different approaches that have been suggested in the past. One is called the synchronous interface, where the operator just watches the live video feeds from all the robots, and that is an obvious scaling problem. Around 12 monitors is what you can do. There's a newer approach is asynchronous interfaces where the robots roam free and they record the videos, and then the operator watches them as they see fit, and that takes the pressure away from the robots being driven around, but it raises the question of what to watch now. And one of the best interfaces for this was done at University of Pittsburgh in joint work with Carnegie Mellon, and they've worked what we nicknamed the best first interface, in which they actually have all these images stored in a queue where the queue is prioritized next to computed utility. So apparently the idea is that you get images based on what you haven't seen before, and this allows you coverage of the work. What we've seen though is that the user actually sees a map, and the best first interface does not allow you interaction with the map and does not use the opportunity afforded by that. So in our interface, which is user guided, we're actually going a step backwards from automation, and we allow the user to click on the map and actually try to identify areas that he thinks it might be interesting. And the key challenge is then to pick up images that contain the point on which you clicked. This is not the same thing as Google Street View, because you're not clicking on the GPS point and getting the image from the GPS point. You're clicking on an image, for which there is no GPS, by the way, and you're trying to get all the images. You're clicking on a point, you're trying to get all the images that have that point within the visibility polygon. So we've experimented with this design versus the best first design. We've carried out significant experiments with 32 participants on 2 different maps in different orderings, and it turns out that our interface works somewhat better. In fact, what really is happening is that our interface remains at a constant level regardless of the size of the map, while the other interfaces actually degrade in performance while the map gets bigger. And for more information, I would love to see you all at the interactive presentation tomorrow morning. Thank you.
Hi everybody, my name is Arne Rönnau from FZI, Research Center for Information Technology in Karlsruhe, Germany. I am presenting the work and the name of the authors. Ming unfortunately cannot be here, so I'm presenting their work on contextual, text-aware, shared autonomy for assistive mobile robot teleoperation. So what is the motivation of this work? We want to relieve the workload of a teleoperator and therefore improve the task performance, especially for mobile robots in unknown and dangerous environments. The approach is based on a model of the user intention. Actually, we're using a contextual task model here, and this is used to provide motion assistant based on this task recognition. And in this paper, we are focusing on two tasks. As you can see, is the door passing on the left and the object inspection on the right. Then we developed a contextual task reference model, as you can see here, which is then used to recover the intention of the user inputs and create a task belief value. So we're using the state variable x, which is put together by the task type and the task feature, and then based on a recursive Bayesian filter and Gaussian mixture regression, we are able to determine the belief value for the two tasks, door crossing and object inspection. I can show you here quickly. So this is all done in simulation for a UAV situation. So you see here the door passing, and the second task is for object inspection. So you try to keep the distance regular for this scenario. So we model these two tasks by creating task features, as you can see here. And before I want to show you some results of our work. These are three scenarios. So first of all is the doorway crossing, and you can see two bars. These bars represent the belief. And the arrow indicates where the user really wants to go. So you can see that this approach is able to estimate where the user intention is gone. And what we use this for is then to apply a motion assistance. So there's a shared autonomy between the user inputs and a model to improve the teleoperation. So you see here now it's the inspection. And as last scenario, you will see a combination of both. Doorway and inspection. Come by tomorrow and see some more details.
Hi, my name is Elias Mügler, and I'm giving this talk on behalf of Gabriele Costante, who unfortunately cannot be here this week. His work was conducted at the University of Perugia and is on a transfer learning approach for personalizing vision-based gestures interfaces for human-robot interaction with UAVs. In this work, we are looking at commanding a quadrotor using gestures. Now, if we learn a general classifier using samples and let a new user try the system, we observe that it will perform relatively poorly. This is because a different user will execute the gestures differently, for example, at different speeds. However, if we have to learn user-specific classifiers for each new users independently, that would require great effort due to the need of collection of enough training samples per user. So we are asking ourselves whether we can use the gestures of previous users or even data from the web to reduce the training effort for a new user. We propose to use a transfer learning framework which results in user-specific classifiers that only require 2 to 3 samples per class. So we learn a set of distance functions where we try to keep the gestures of the same category close and push away gestures belonging to other categories. We also constrain the optimization problem using previous data. However, we only do so if the similarity between the user data and the previous data is high enough. This is important to avoid transferring harmful information. We used the CAC gesture dataset together with the dataset we recorded ourselves to test different combinations of source and target data. We implemented a complete human-robot interaction system with an AR drone. The system first detects the person and identifies it using face detection. Then it loads the corresponding gesture models that were learned offline. Once it detects such a gesture, it sends the appropriate command to the drone. If we look at the results, we see on the left that the performance is relatively low if we only use web data or data from previous users, so up here. And so that is a generic classifier. If we only use the few samples that we have from the specific users, the performance is also about on the same level. However, if we combine all available data, the accuracy increases significantly. And I will be happy to show you more details of our approach during the interactive session, and there I will also have a video showing the system in action. Thank you very much.
Hi, my name is Vivian Chu. I am presenting work on contingency detection for HRI. This is work done jointly with my colleague Kalisha Bullard under our advisor, Dr. Andrew Tomas from the Socially Intelligent Machines Lab at Georgia Tech. As robots become more prevalent in society, we have to start thinking about how humans and robots interact. However, before you can even start looking at the human-robot interaction, you need to know whether or not the person wants to interact with the robot. Typical approach in HRI is to treat this as a person detection problem. So essentially, once the person is detected, the interaction starts, and once they're no longer detected, it stops. However, what you really want isn't a person detector. What you want is a robot to find an interaction partner, someone who wants to interact with the robot. To tackle this, we treat this as a contingency detection problem. A contingent response is a change in one's action within a specified time window due to some external signal. This is a key component of how infants start to recognize social agents. To do this, we took an approach where we took the robot and we have the robot signal to a person once they're detected. And then within a specific window, we detect whether or not there's a human response. We want to detect any sorts of response, and then we want to do this in real time. To do this, we look at two separate types of data. We look at the stereo audio channel as well as body pose from a body tracker, from a skeleton tracking on an RGBD sensor. We basically, when the robot signals, we look at the data before the signal and after the signal and compute the change in sensory input from both states. We collected a data set where we have various users perform different types of contingency reactions, and we trained a support vector classifier that can detect whether or not there's contingency. The last part will just be a video of my colleague actually interacting with our robot. What she says on the bottom, what the robot says on top. Curie detects Kalisha in the scene, waves, and Kalisha engages with the robot. The robot correctly continues the interaction because the detected Kalisha wants to engage. We have the exact same scenario where instead of having, where the robot detects Kalisha in the scene, signals by waving, but instead of continuing the interaction, realizes that she doesn't want to continue to interact and ends the interaction. We have a similar scenario where instead of just standing from the robot, she approaches the robot, and we use a verbal signal this time. Finally, Kalisha ignores the robot and just continues to walk past. And the interaction is ended. To find out more about how we actually do this and how the robot performs with users not in our training set, please come to the interaction session tomorrow morning. Thank you.
Good morning, good afternoon, sorry. I'm Kai Yu from Rutgers University. Unfortunately, the author of the paper cannot make it to the conference. Hereby, I'm here to give a brief insight of pose estimation in physical human-machine interactions with application to bicycle riding. Bicycle is not only a popular transportation tool in our daily life, it can also function as a highly dynamic and unstable platform to study human and machine interactions. In addition, it can also be a potential rehabilitation device. It is very interesting to find that the patient with Parkinson's disease who can barely walk, but he can ride a bicycle like people who doesn't suffer from any movement disorder. Therefore, accurate pose information for a rider bicycle system is very crucial for clinical analysis and also for understanding the physical human-machine interactions. However, field work were reported to study the outdoor whole body pose estimation for rider bicycle systems. Therefore, our goal here is to provide this kind of estimation strategy with few number of variable sensors. And this kind of scheme can be extended to other physical human-machine interactions. 2MUs and 4 gyroscopes are fused with encoder and first sensors data using an extended Kalman filter technique. We also incorporate a physical and geometric constraints to reduce the number of sensors. Here is a basic structure and data flow of the EKI fusion to estimate the pose of both bicycle and human pose. When compared with the ground truth vision data, the proposed scheme can accurately estimate the human whole body pose in real time and also give a drift-free result when compared to the integrated gyroscopes measurement. Also, the effectiveness of the whole algorithm can be validated in both indoor and outdoor experiments. And more technical details will be given in the interaction section. And thank you for your attention.
Hello, my name is Yasemin Bekiroğlu. I'm with KTH and I'll talk about our joint work with EPFL. We study grasp adaptation strategies based on learning and tactile sensing to deal with uncertainties about object properties such as weight or friction at the contact points. And the aim is to keep a grasp stable after it is executed. In the experiments, we increase the object weight or the objects are disturbed by a human. And during these changes, once the grasp is estimated to be unstable, there are two strategies that are selectively triggered. First, we try to adapt stiffness, which means regulating contact forces indirectly. If the current grasp is not similar to the ones in the training data, then another strategy called local exploration is triggered. And in this step, a finger explores its local area by changing its location to reach a grasp that is similar to the ones it has experienced before. So here in this example now we are seeing more of these cases. I can show you more of these tomorrow. At the end of this local exploration step, stiffness is changed again, and this procedure is repeated until we reach a stable grasp. We have a learning approach, and the data that we learn from contains tactile readings, stiffness, and the rest length. The rest length is the distance between each fingertip and the center of contacts. This way, we don't use explicit information about object geometry. And at every step of our approach for stability estimation, for the prediction of desired stiffness or local exploration, we are using Gaussian mixture models that we learned from the data. For instance, in the local exploration step, we move the current grasp configuration towards the closest center of the Gaussian components using rest lengths. Some quantitative results. We compare the maximal object weights that a grasp can support with and without our approach, and we see that we have significant improvements using our approach regarding the maximum object weights. And I can tell you more about these results than our the details of the modeling using Gaussian mixture models tomorrow. Thank you very much.
Hello, my name is Sonia Chernova. I'll be presenting work on the construction of an object manipulation database from grasp demonstrations. This is work led by David Kent. This is his master's thesis or part of it. He wasn't able to make it today due to illness. So the main objective of this work is to improve the ability of robots to identify and manipulate a wide range of objects. We're particularly interested in household domains where there are many new objects and no specialized equipment to develop precise models of the objects that are being encountered. So our contributions are an object manipulation framework that allows for easy addition of novel objects, requires, oh, I'm sorry. I never noticed that you see all my slides. Requires no equipment beyond the robot and is usable by non-experts. It leverages also demonstrations to compensate for difficult to observe information. So here, our paper builds on prior work, which is in which we collected object models and grasp information from the web. So on the top, you see the physical robot setup. On the bottom, you see the interface that people were using. We had participants that had no robot experience. They were at their own house, and they were using the web browser to control the robot, pick up as many objects as possible within the time. The output is the model you see on the right, with the grasp points mapped onto the 3D model. To build our database, we first construct the object model through point cloud registration. We filter out any outlying grasps and estimate the grasp success rate and then rank the remaining grasps. The way we actually do the estimation is online. So here you see pretty much the entire process takes about 5 minutes. The robot performs exploration of the grasps as their options and then ranks them based on success. Once that's complete, here's how the robot picks up the objects that it's able to grasp. It's pretty much perfect performance. If it misses something by accident, it's able to use one of the other grasps in the database. We compared performance on a wide range of objects. Our results are plotted in red and blue for different groups of demonstrators, but our performance is pretty much on par or better than the standard PR2 grasp mechanism. Where we really see the big gains is when we work with difficult to grasp objects, such as ones that have uneven grasp weight distribution or have fragile parts. And here we can really leverage the knowledge conveyed by human demonstrators through their grasp selection, as well as our online grasp refinement process. So that's kind of the red line at the top. Thank you very much.
Hello, my name is Alex Goins. I will be presenting our work on evaluating the efficacy of grasp metrics for utilization in a Gaussian process-based grasp predictor. Traditional grasp planning methods use grasp metrics to plan stable grasp. However, due to correlation among the metrics and limited experimental validation, the overall performance of many of the metrics is still unknown. Furthermore, these metrics only provide a relative measure of grasp quality. In practical terms, we would like to have an absolute measure of grasp quality to facilitate grasp planning. To this end, we compared 12 different grasp metrics found in the grasp planning literature to determine the ability to predict grasp performance. We then use a machine learning technique called Gaussian process to combine the most discriminative grasp metrics to create a grasp planner which outperforms the individual metrics. Using 9 everyday objects, the three different control interfaces, we collected a large grasp set from 22 human subjects. The grasps were created in an open source simulator, OpenRave. From simulation, the 12 grasp metrics were computed and the grasp orientation and position were recorded for later execution. We then executed the grasp on a Barrett-WAM system to determine the grasp performance. The object is grasped with extra precaution taken to recreate the grasp exactly as it was planned in simulation. This was done to ensure that the grasp test on the physical robot corresponded to the grasp as was originally created in simulation. Next, we created several simple classifiers using the metrics independently to determine their predictive ability. In order to have a successful grasp planner, we examined the lowest false positive region in order to minimize the number of failed grasp attempts. Looking at the true positive rate for each metric, we found that many of the grasp metrics have low predictive capability when used individually. Finally, we used the most discriminative grasp metrics and the grasp test results to create a Gaussian process-based predictor. Looking at 2D prediction of the multidimensional classification region, we can see the GP classifier is able to create a non-linear decision surface capable of discriminating between successful and unsuccessful grasps. Comparison of the GP-based predictor shows that it's able to improve the classification performance over that of using the best performing grasp metric individually. which is especially evident in the low false positive region. Furthermore, because of the training using physical test data, the GP classifier provides for an absolute measure of grasp quality for plane execution. In conclusion, we compared 12 common grasp metrics and found that many have low predictive capability when used individually. We use a Gaussian process-based classifier to combine the most discrete metrics, and we're able to create a grasp classifier which improves over those metrics while providing an absolute measure of grasp quality. If you'd like to know more about how we created the grasp predictor, please see me in the interactive session tomorrow morning. Thank you.
Hi, I'm Oliver Cromer, and today I'm going to be talking about predicting object interactions from contact distributions. This is joint work together with Jan Peters, which was done at the TU Darmstadt. Different contacts afford different kinds of interactions with objects. So for example, if we have a contact on the side of an object, we can use that for pushing, whereas if we have contacts on opposing sides of an object, we can actually use that for pushing and grasping. In order for a robot to perform a wide range of different interactions or manipulations, the robot should learn which contact distributions afford the desired interaction manipulation. Given that similar contacts afford similar interactions, we propose using an example-based approach. In particular, we propose using kernel methods to predict interactions. A kernel is a function which defines a similarity between different examples. So in order to actually use kernel methods, we first need to find a suitable kernel function for contact distributions. Let's assume that we want to compute the kernel between these two grasps. The first thing that we do is we take the models of the hand and the object as shown here, and we use these models to compute the contact points and their corresponding normals. We can then fit a 6-dimensional Gaussian to the contact points and their normals as shown here, and these Gaussians we refer to as the contact distributions. Given the two contact distributions, we can then overlay them and compute the Bhattacharya kernel, given by the equation down here. Intuitively, if the distributions are identical, the value of the kernel is going to be 1. And as the overlap between the distributions decreases, the value will tend to 0. Using this kernel, we were able to predict stable grasps of objects using kernel logistic regression and achieved 95% accuracy. We also used this kernel together with spectral clustering in order to segment grasping movements, and we were able to detect the different phases of grasping. Apart from grasping, we also looked into stacking objects. So here you see a robot and is currently observing the scene. It sees this point cloud. It's now going to sample different locations where the object might be placed, and it's going to choose the best one of those and execute it, as you'll see in just a second. So using this approach, the robot was able to perform several different, create several different towers, including the one shown in the video here. For more information about the proposed method, extensions of it, and more information about the results, please come by the poster session tomorrow, and I look forward to seeing you there. Thank you.
Hello, I'm Yevgen Chebota, and in this work we explored how to learn robot tactile sensing for object manipulation. In particular, we developed several components that are needed for tactile-based manipulation, and I would like to start with the hardware. In this work, we used a low-resolution and low-budget tactile matrix array and placed it on the parallel gripper. We used this setup for performing localization of several objects inside the robot hand. It could achieve the best results with a probabilistic voting scheme by having an accuracy of about 1 tactile. In the next step, we used imitation learning and in particular dynamic motor primitives to actually learn the motor skills of the robot from demonstration. Furthermore, we augmented the dynamic motor primitives with tactile feedback that ensured that the robot stayed close to the demonstrated tactile trajectory. We learned the weights of the tactile feedback with reinforcement learning. However, by doing so, we encountered a problem of very high dimensionality of the tactile data. Therefore, in the next step, we performed dimensionality reduction and first of all used principal component analysis to detect and use only the changing parts of the tactile images during manipulation. Second, we used similarity values of tactile images to recognize phases of the actions and motions, and actually learn only a single feedback weight for each phase of in the manipulation task. In our experiments, we performed a simple manipulation task. In particular, we placed a spatula inside the robot hand and demonstrated a gentle scraping movement with the spatula along the table surface to the robot. After that, we changed the environment by elevating the surface of the table and placing a ramp on the table. And the goal of the robot was to adapt to the adapt to the changed environment by staying close to the demonstrated tactile trajectory. In order to learn the feedback weights of the tactile information, we used a relative entropy policy search algorithm. So in this video, you see the performance of the task without any policy updates. The robot goes too far towards the table by trying to stay close to the demonstrated motion and doesn't control its height very well. In this video, the robot performs the task after 6 policy updates of the tactile feedback weights. He is able to control its height and adapt to the changed environment. For more details, please visit our interactive session tomorrow morning. Thank you.